Welcome to Study Loop.
So in this problem, we have a, a copper calorimeter can, and it has a mass of 0.1 kilograms. It contains 0.16 kilograms of water and 0.018 kilograms of ice. It's all at atmospheric pressure, so we don't have to worry about pressure considerations in this problem. And then we drop a hot piece of lead into this, and the lead weighs 0.75 kilograms, and it is initially at 255 degrees C. Now, we're told that the water and the ice are in thermal equilibrium, which means that they're both at 0 degrees Celsius. And then T2, I'm going to call for the temperature. So we drop this in. We have this copper, and then we have this water with some ice in here. And then we drop this lead in here, and then we let it all come down to thermal equilibrium, and we want to figure out what the final temperature is. And we're assuming that basically this is all insulated and we get no energy loss outside of the system here. So basically, this energy balance, it says that, the energy before we drop the internal energy before we drop the copper in has to be the internal energy afterwards. And all these internal energies, because we have, solids and liquids, we're just going to say that we have a constant heat capacity. So there's just a constant heat capacity times the mass times the temperature. And so then, we know the change is then we wind up with changes in temperature. The other piece that we have to be very careful about and not forget to include is the heat of fusion for the ice. So the ice is going to melt before it starts to rise for its temperature to rise. So we actually have a lot of energy going into melting this ice, as we'll see in a second here. So we need to make sure we keep that. And this is I used a U. I'm not sure what the notation they used in the book. I think maybe they used Q for this heat of this latent heat of crystallization. No, whatever it is. This latent heat going from a solid to a liquid. I just lost the name of it in my head. Anyway, latent heat of fusion. Fusion. Yeah. There we go. And so then we have the change. This is the change in internal energy in the lead, in the copper, in the water, and then the ice winds up being changing from ice to water, and then from water as it goes up in temperature to equilibrium, it's then water. So what we need to do is we need to look up all these heat capacities, and we can do that. They're all listed in the book. And then we can use degrees Celsius for these temperatures because they're temperature differences. Again, it's a little bit. It's probably better to just convert everything to Kelvin, but in the end, a change in Kelvin is equal to a change in degrees C because the difference is just an offset, not a factor. So we can use degrees Celsius in this problem because we just have changes in temperature. So we don't really need to do the Celsius to Kelvin conversion. So we can see here that the heat capacity for lead is 130 kilojoules per kilogram Kelvin. And let's see here. That's actually pretty low, right? If we look at what it is for water, the heat capacity of water is actually very high. This is why we use water to cool things a lot. Now, so then the change in temperature, it's at T2 finally, but it's initially at 255 degrees Celsius. For the copper, the copper heat capacity is 390 kilojoules per kilogram Kelvin, so 3 times that of lead. Then again, the heat capacity for water is 4,190, so almost 10 times what it is for copper. And so again, the copper, we're assuming that the copper is also at 0 degrees C, so it's in all thermal equilibrium with the water, the ice water. So those are all at 0 initially. and then they end up at T2. And then we can look up the latent heat of fusion for water, and that's 334 times 10 to the third kilojoules per kilogram. So that's pretty high. It takes a lot of energy to melt ice or to freeze water, and so that contributes quite a bit here. And then after the ice melts, then it gets raised up from 0 degrees C to whatever the final temperature is. So again, we have the mass of the ice and then the heat capacity of water. And so, and that how it has to be 0, because the energy before has to be equal to the energy after. So this whole equation, we know everything in here but T2. So it's just a matter of plugging in numbers and solving for T2. And we get that it is a temperature of 21.4 degrees Celsius is the final temperature of this, of everything, of the copper, the water, the ice, the ice which is turned into water, the lead, and the lead are all at 21.4 degrees Celsius. And again, that is assuming that this whole thing is insulated so that no energy was lost to the environment as this was cooled.